Okay, pre-semester, let's go. I did differentiation last time. Now let's do some examples. So gradient example. Let's say that f was equal to z. No, just z, not z. Actually equal to z. If I did the gradient of f, of course, there's no, the others, x and y are going to be 0. So this is going to just be z hat. And that, of course, makes sense. The steepest, if my function is z, of course, the steepest path is up z hat, right? Okay, what about the radial direction? So let's now say that f was equal to x squared plus y squared plus z squared. And that is, of course, the distance to the origin. So we have square of that. Now, let's see if the function is the distance to the origin. What is the steepest path then? Do the gradient again, which is partial f in terms of x in the x hat direction, partial f in terms of y in the y hat direction, and partial f in terms of z in the z hat direction, right? The easiest thing we can do, if I just do this component-wise, I do the x component here, then we can just do, you could see I can do partial in terms of x, right? And then I have x squared plus y squared plus z squared. That's, of course, and 1/2. That's simple integration. Of course, this guy gets negative, so we just do it like this. 1/2. 1/2 there in front, of course, and the chain rule, 2x. And in the end, this is just x over r, like that. Which means that we get the same result for each of these pieces. Which means that we get, of course, just x over r, in the r hat, in the x hat direction, plus y over r in the y hat direction, plus z over r in the z hat direction. Now this x plus y plus z is, of course, just the vector r divided by r, which is r hat. Again, the steepest path is now in the radial direction. Why? Because our function, of course, is distant to the origin. Perfect. Okay, now let's keep on going. Now we can do some, we did divergence last time, so now let's do some divergence examples. I haven't written down the examples you have to see in the book. We can just take the first one and I can explain a little bit. Let's see, it's, here it is. Yeah, we can do this guy. So in figure 1.113, illustrate the 3 vector fields, blah, 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 find divergence of these fields. Right, there's no x, y, and z here, just f0. So this field is just a constant in the x direction, and there's no divergence, of course. Divergence measures, right, if I have some box, if I have a vector field like this, and I place a box, and I place a box at some point here, the divergence is a result of how much went in and out of that box, right? But you see, this is a uniform field, so of course there's no divergence, right? But if, let's say, I had more vectors, I don't know, here for some reason, then there would be a divergence there. There would be more coming out than there were coming in, right? It will be a higher strength here compared to here, right? Okay, and that's all right. We can just look at that vector field, see if that's true, and that is indeed true, like that. Okay, yes. Now we can go to something cool and very useful, the divergence theorem, right? The divergence theorem is pretty useful and pretty cool. It states that if we took, let's see, divergence and flux, of course, and if I took now f that's multiplied by ds, like that, and it's of course over a surface, that is actually the same as, again, we take the line integral for f, and we now do Not the line integral. Is that... oh, it's not the line integral. You moron is, of course, I integrate over the volume, divergence. And then I do the divergence, which is just nabla dot f and over the volume, the volume, like that. The volume, of course, is not... what you call it? The volume shouldn't be, in my opinion. Yeah. This guy multiplied this guy is a scalar, and this guy multiplied this guy is a scalar. Yeah, that's correct. Okay, now which one of these is closed? I don't actually remember. The left side here is of course the flux. Flux don't need to be a closed surface, but then again, one of these is going to be a closed surface. I have a 50-50 chance here. I'm pretty sure that one of these is a closed surface. I would guess that it would be the flux, right? Not the right component. If we have, let's say, the volume, does the volume has to be? No, I think the volume has to be closed. I feel like the surface, but my brain is like, no, it should be the volume for some reason. But the volume internally would cancel out. Oh, no. Closed surface. No. There you go. It should be closed surface. Let's see. It should be closed surface. It has to be closed surface. Yes, it's closed surface. Yeah, you can't close the volume. What are you talking about? It's closed surface. All right. Okay, perfect. Okay, so now let's do some intuition here. This formula is actually pretty easy to understand. It states that the total flux, which is the global property, is the same as collecting all the little. It's very much like the fundamental theorem of calculus. So the total flux is like collecting all the small pieces of flux, which is of course divergence. So all the local flux divergence, if you collect all of them, actually turns out that that is the same as the flux, right? And we can draw that with a simple image. So if I had, let's say I had, here is my surface, right? I can just to make this clear. This is the surface S, right? Now I have my small pieces, like I have these boxes that I have drawn to represent divergence, right? And this belongs to the volume, right? Okay, so I can just drew them in 2 dimension. You get the idea. It's the same no matter what. So I have the boxes here like that. Now this guy like that, and that guy like that. And divergence, goes out in all the directions. So here, there's a vector there, there's a vector there, there's a vector there, there's a vector there. But similar, there's a vector there, there's a vector there, and this is starting to get quite messy. But it will make sense pretty soon. So what is actually happening here is that these that are next to each other will cancel out. That's pretty clear. You can see this guy will cancel out, here it will cancel out, and here it will cancel out. And if I drew the rest of the boxes here, you will see that all the volumes will cancel out, except the sides that are, of course, touching the surface. Which means that if we collect all of the boxes and their divergence, we get, of course, the flux that passes through the surface, right? Pretty neat. Okay, so that's the divergence theorem. Now, in light of divergence theorem, we are of course going to jump into curl. So curl, divergence and flux, very similar to curl. And of course, what we're going to have is something called circulation and Stokes theorem. So let's start with curl. So curl is the local circulation. Same we had with divergence. Like divergence is of course the local local flux, right? Flux is the global property, but curl is the local circulation. And circulation is just the same line integral that we had, but closed. So we just have f, and that multiplied by, of course, the L, like that. That is what we had to represent. We had it to represent work earlier, but for a closed loop, we have circulation. This means that if I have some curve like this, but it's going to be an object because you can actually take it in 3 dimensions, but this still applies. So I have this object. All of this is the object. I just used blue here to represent the path, not S, you moron. It's of course over the curve, and the blue here is the curve, like that. Okay. So circulation, this integral, is the tendency to circulate. It's the tendency for the vector to circulate. If I placed my boat here, and my boat moved some dl, will the vector field here cause it to circulate? That is what this measures. If I did this, of course it wouldn't circulate. It would actually diverge, like it will move outwards. But if the vector field was like this, my boat would circulate, right? Okay. So how does this relate to what we call curl? Curl is the local of this guy. So if we took this guy and just shrinked it to a point, that is what curl is. And of course, to measure curl then is then instead of measure on this big curve, we just measure in a point. And if you measure on a point, I would rather just place a propeller there and see if this propeller would, like, how can I do that? Yeah, rotate. Yes. Yes, that is what I'm asking. So if this propeller rotates, then our vector field would maybe, let's say if our vector field were something like this, right? Then our propeller would, of course, rotate. And this, of course, is a vector because we have, with the right-hand rule, we have pointing upwards. This is a positive direction, right? For rotation, you know, rotation, of course, has direction. So that is what curl is. And if we take something global and zooming in, we can use this intuition formula we had earlier. So same idea as the divergence. So if I take the limit and I let, of course, now instead of the volume, I let the surface, so the change in surface, I let that be pretty small, right? Or do I want the curve? I can let the curve too. Maybe I think I stick with the surface. I think that's more correct. And let that be pretty small. I should actually write that the curl, the tendency for the vector field to curl in the z direction, just to be neat, is equal to the limit as the change in s goes to 0, right? And again, it's a factor, right? It's a ratio, I mean. And then we take the same line integral over that closed loop. And it will, do we take the surface integral? Yeah, we take, of course we take this integral. So I take the line integral and I let this guy, do I want the surface integral maybe? Do I want the surface integral? No, that wouldn't make sense. Shouldn't I make, maybe that guy should be small? Oh, let's see. Now I let delta s be small. I think that would be correct. I would have dl still, and I just let s be small. Yeah, that should be correct. We are doing essentially the same thing, but for something very, very small. That should be curl. I think that's correct. Let's see. Yeah, not the diverge. Blah, 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 blah. Yes, I know, curl. Yes, that's correct. Yes. Okay, my intuition was correct. That's good. That's the point of doing all this. That's the point. Okay. Very good. Very nice. Yeah. Okay. So the formula, then I have derived this formula before, so I'm not going to do that again. But the curl of f is just equal to the nabla, and then instead of dotting it, we're just crossing it with f, like that. Okay, we can calculate the formula as well. Remember that this is the same as I hat, j hat, k hat, and then of course I would have partial. In terms of x, I will have partial. In terms of y, I will have partial. In terms of z, and then of course I would have f, the x component, f, the y component, f, the z component, like that. Okay. And that's just, we do I hat, then of course cross that out, partial of f z with respect to y, and it's always the opposite, so that will be partial of the y component with respect to z, and then I will of course have minus j hat, j goes away, and I have partial in terms of f z component with respect to x minus, and then of course partial of the fx in terms of z, then I would have plus k hat, last one, and that's just partial k hat partial f y, and the last one is of course x minus partial f x component in terms of y, like that. And usually you just flip things around there just to make things more neat. So partial f z in terms of y minus partial f y in terms of z, comma, I turn this around and I get partial fx in terms of z minus partial f z in terms of x. Nice. Then of course I have partial f y, and then in terms of x minus partial f x, and then in terms of y, like that. Pretty neat. Okay. So like I said, I've done the proof, and my intuition behind this formula here is that we are doing derivative. Remember, in order to go around, what it actually means to, what we know from centripetal acceleration is that what it means to go in a circle is change, right? You need to do some kind of derivative when you go in a circle. It's the change of direction in order to go in a circle. So I think, okay, we need some kind of derivative, right? And in order for us to circulate, we need our vector field to go like this, right? We need them to compare to each other, and actually one should be bigger or smaller than the other, like that. And that's why I think we are comparing each of these components like that. What I'm trying to say, right, if I have this propeller, I need this guy to go like this, but then I need this guy to go like this, right? And then the one below to go in the opposite direction and like this, right? So I need this kind of behavior, right, in order to circulate in a point, right? Okay, that's just the way I think about it. Right, now let's see. We have Stokes' theorem. Let's see, actually, Stokes' theorem, I can use my beautiful image here, because that will work very well. Copy, and then paste. Then we could have our little line integral here, which was f dotted with dl over c. That was equal to, this is the Stokes' theorem, the integral over the surface, and we are integrating, of course, curl, which is just nabla, cross f, and then of course ds, and that has to also be a vector, of course. Yes. Okay. This is also pretty neat. This also tells me the same thing. So if I have, let's say I'll draw on my surface here, this is some point where I have curl, right? So curl, of course, with the right-hand rule, the normal vector would be the size of the curl in this case. We have some vector here, it's pointing upwards, right? And I can draw all of these normals on that surface. So if I actually took now and drew all of these, and I would have looked at the curl, the tendency to curl everywhere, something interesting would happen. Same as last time. So if I have, this is my surface here, I just drew it in 2 dimensions, and I looked at every place it wants to curl. I can draw that in green. That will just make more sense. Like that. Okay. So here is my, like, the places where I look at curl, right? Like that. And again, the curl will go like this around the surface. So it'll be the opposite. Instead of going out, it will go around. So I should have another vector. So it will go around, go around, go around. But this guy will go the opposite. Go around, and I should draw a box here as well, and here as well. And you will see that that guy will go the opposite. Go the opposite, and you will see, of course, again, that only the ones that are actually touching our surface matters. And not only that, those will actually also cancel out because they are lying like this on the surface. I am actually mistaken. It's actually only the ones at the bottom that will survive, right? Those have nobody to cancel out because it's a surface. So if I zoomed in here, actually it will be some boxes on the other side on top of the surface, and they will cancel out. So actually, they're only the ones that will be here, right, alongside the curve that will matter. So instead, what you could imagine with my 2D picture, let's imagine that this guy here, let's do the style and blue. So this is now my curve instead. That's a better image. So this is the same as my curve. And here you have all the places where I look at curl, and only the ones alongside C are the ones that will survive. Same thing again. It's like it's for my boat, for the tendency for my vector field to curl, the boat here, right? For tendency for my vector field to circulate, the global property is the same as collecting all the small local circulation, the curls. If I collect all of those, I will get the same result. That is what this statement here means, right? So pretty neat. It's a very neat theorem. And also what's pretty cool is that if you think pretty cleverly, you can see that if it doesn't matter, I could choose this surface or the more three-dimensional surface on top here. Just to make this clear, I could do it like this, right? I could choose either one of them. I will still get the same result. That's pretty neat. I actually think you can do some cool calculations when it comes to the wind of the earth and etc. But we care about the electromagnetism and so. But that's just a small detail. Okay, so that's it. All right, the last thing I have is just something about coordinate systems. We need those as well. Okay, we can just do some simple stuff here. Cylindrical coordinates, of course, pretty simple. You have something like this, and of course, if I want to measure some point here, that's the same as going there and then going there, and in order to get there, I have phi, and I need r, and then I do z up there, of course. Pretty neat. So r is just equal to, of course, r is just equal to r cosine of phi in the x hat direction plus r sine of phi in the y hat direction, and of course plus z in the z hat direction. That's just it. Pretty easy. Okay, so what we can do, which is a little bit more complicated, is look at some things here. For example, we can look at how we can find all the unit vectors for the cylindrical coordinate system. So the unit vector would be here, would be r hat. This around the plane would be, of course, phi hat, and up would, of course, be z hat. And you can just use your intuition here. It's pretty easy. So r hat is the same as r. You just need to remove, of course, r itself. So it's just cosine of phi plus sine, oh shit, I need cosine of phi in the x hat direction, and then of course just plus sine of phi in the y hat direction. There we have r hat. Phi hat is also pretty easy, because that's just 90 degrees to r hat, so you can either take 90 degrees, you can remove pi from the equation, or you can just do the derivative, it's actually the same. So if you do the derivative, you get minus sine of phi in the x hat direction, and then plus cosine of phi in the y hat direction. And z is, of course, just unchanged, like that. Cool. Okay, that's pretty neat. We can also do more cool stuff. We can look at what is the change in volume and what is the change in surface. So if you had some change in surface, of course, that is just the height. So if I took some surface object here, let's say I had some surface object like that. Of course, the height of that surface object is just z. And then, of course, the bottom part is just phi hat, but phi is not a distance, so we can multiply by r. So this means that ds is, of course, just the same, and maybe I should write that as a vector. Should I do that? No. Oh, not z hat, you moron. Ha. That doesn't make sense. Of course, that's just dz. That's what I meant. And d phi multiplied by r. Yeah. So ds is, of course, just dz r d phi, like that. Perfect. Okay, and if you actually want a vector, this is just in the r hat direction. So you can do that as well. Okay, and if you want the volume instead, that's pretty easy, because we still need dz, need r, and we need d phi, but now we also need, of course, dr, like that. That's the volume. Neat. Okay, let's continue on. So now let's describe vector fields in cylindrical coordinates. Okay, so if I have a vector field in Cartesian coordinates, let's say I have my vector field E, x, y, and z, like that. That's just E of x, y, and z. Of course, in the x hat and etc. I'm not going to do the rest because it's boring. You get the idea. But now I want to describe the same vector field with cylindrical coordinates, so I should be able to do the exact same thing. Coordinate system don't care if I describe a point. If I get to the point using a cylinder or a sphere or Cartesian coordinates, that doesn't matter. I get to the same point. That's what matters. So this is just r. So this is the same as r, phi, and of course z. And I need to describe this the same way. So E of r, x, y, and z, and of course now in the r hat direction, and etc. So how do I do that? I need to go to, of course, cylindrical coordinates the same way. Okay. So we want here we want to represent the unit vectors for cylindrical coordinates that we want to do. Okay. Let's see. I have r, phi. Yeah, I did that actually last time. Yeah, I actually did this here. So now I have the unit vectors with cylindrical coordinates, pretty neat. And now I also want to go back to Cartesian coordinates. And that is, you can do one simple trick. I can look, okay, for r, how is he contributing to the x direction? Yeah, it's just cosine of phi. So x hat is just cosine of phi r hat. And then I look at phi, and phi, of course, for in the x direction, it's just minus sine of phi. So minus sine of phi in the phi hat direction. I can do the same thing for y hat. Y hat is just sine of phi, and then of course in the r hat direction. And then I just have plus cosine of phi in the phi hat direction. And z is just still boring z hat. like that. Cool. Okay. Yes. And now we have everything you need. There's some example from the book, but we don't need to do that. Let's see, where's that example? Stokes theorem, blah, blah, blah. Yes. Yeah. Yeah. So this is just the example. You just plug in, it's pretty easy. So it's equal to this, E0, so just plug in. We already did the calculation here for this. You can just plug that in, and the same with phi hat there. You can just plug that in. And then if you want, like we did now, to go back, I can just substitute, right, and get this kind of vector field instead. But it's the same thing, of course. Awesome. Now, let's do linear algebra. Okay. I should actually have that book in front of me. This is a linear algebra. There you go. Column space, etc. Yeah, that's all right. Okay. Let's see linear algebra. So now, let's get my notes ready here. Okay, in linear algebra, we're going to start with null spaces, column spaces, row spaces, and I skip linear transformations for now. Let's see, the null space of a matrix. So what does that mean? Let's say we now had a homogeneous system of equations. For example, if I should have that one for a book because we actually need an example, or I can just do one myself. So for example, if I had 3 times x1 plus 2 times x2 and minus 5x3 is equal to 0, and 1 x2, why did I write 1? Yeah, and x2 as well. x1 minus 5 x2, of course, and plus 3x3 is 0. So this is, since we have 0 here, this system of homogeneous equations is what we have. And since it is that, we can write it as a matrix. So this is actually this equation here, which is equal to 0, the 0 vector. And A, the matrix A, is now, of course, just 3, 2, minus 5, 1, minus 5, and 3, like that. And the set, the set of all the x's, so the set of all the x's that satisfy this equation is called the solution set. But even more importantly, it's a space, and not just any space, it's a null space. So null space is the space of vectors that satisfy this equation here, right? That is what we want. Okay. Let's see, I need that example. That's why I actually should have just looked at it, but it's all right. Where is my... oh, I have this neat way of doing this. There we go. So I need, instead, I need 1 minus 3 minus 2. Okay. Let's do that instead. 1 minus 3 and minus 2 minus 5, 9 and 1. Right, and what we had was the example, blah, 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 definition. Okay. Let A be the matrix and let U, and then determine if U belongs to the null space of A. That's pretty simple. We have 5, 3, and minus 2. Just move this guy here. So we have U is equal to the column vector 5, 3, minus 2. Like that. And to check if it's a null space, let's just run that vector through. So A, U is equal to, so we get 5, 5, and then I, of course, get minus 9. Whoops, I should have done minus 9, and then I get, of course, minus 2, plus 4, then I get 5 and 5, minus 25. Am I doing this correctly? Yeah. 3 and 9, That's of course, yeah, that should be correct. Yeah, of course, you get 3 and 9. That's of course just plus 27. Then you get -2 and -2. Yeah, you see this guy goes out, this guy goes out as well, and we just end up with 0, the 0 vector. So this guy, U, belongs to the null space, right? Okay, perfect. That's what I want. What is the next thing I have written here? And that's the, yeah, we need the theorem to which I stated that the null space is a subspace and not just, I'd say that it was a space, not a subspace, but it's a subspace and not just any subspace. You could see in this case, it's a subspace of R of n, right? Because we have, of course, this is a m by n matrix. So we have m by n, right? So it has, it of course is, as you see, it's a subset of Rn, right? Because we have 3 columns here, right? And this is a 3-column vector. Okay, so it's a subset of Rn, right? So to do the proof, we first recognize, like I said, that null A is of course subset in our case of R of n, right? And I need, of course, that to be correct. I need R of n in our case. And since 0, this is not perfect, but you get what I mean. Since 0, of course, is in null A, so 0 is in null A, we can just pick any vectors in null A, like u and v, and we can write that AU is, of course, equal to 0, and AV is equal to 0. And of course, 0 is in the null space. So if A is a null space, no, not A, no more. The null space itself. Oh my god, what I'm stating. Since 0 is in the null space, the first requirement is satisfied. Now, in order to show the second requirement, which is addition, we can use what I've written here. Because if I write A of u plus v, you would see that we get AU plus AV, which is just 0 plus 0, which means the second one is true as well. We added 2 vectors, and still we're in the same space, right? Okay, and I can do the same thing for, of course, a constant. So A times CU. You can not move vectors around, but constants you can. So this is the same as C, A, U like that. And of course, this is C times the 0 vector. And of course, it's just a 0 vector. So all of them are true. So indeed, the null space, of course, it's a subset of R of n, right? Okay, that also means equivalently that the system, or the set of all the solution to this system, A of x is equal to 0, is also a subspace of Rn, right? So null, and it actually means it is just the same thing, right? Okay, now let's move to example 2. I just wrote example 2, so we have to check what it is. Yeah, I just did this proof. Very good. That was my argument as well. Same here and same here. So very good. Yes, there we go. Example 2. Okay, so let H be the set of all vectors in R4 whose coordinates A, B, C, D satisfy the equation A minus 2B plus 5C is equal to D and C minus A is equal to B. Show that H is a subspace of R4, right? Okay, so we have the equation. We have 2 equations. We have A minus 2B plus 5C is equal to D. Then we have C minus A. I can just write that more cleverly. Minus A minus B. And then I have, what was it? Plus C is of course equal to 0. I want to show that this H here is a subspace, so H is all the vectors that satisfy these 2 equations. And I can, of course, do this now. So if I instead took d over there, minus d, and I just wrote plus 0 here, equal to 0. Now this can be, of course, represented as a matrix. And of course, that matrix you can see already, because this equation is now satisfied. And of course, H is now a subspace of R4, because this is a 4-dimensional. Of course, this is... did I write that correctly? A subspace of R4, isn't that correct? Yeah, m times n, right? Yeah, our vector has to be of, yeah, of course, of 4 components, yeah. So that is entirely correct. Perfect. Let's see, yes, yes, the same thing with theorem 2, H is subspace of R4, yeah. Very good. Okay, now let's see the column space of a matrix. Also something very important. Okay, we know that we can write a matrix as a m by n matrix, right? And it has n columns, which means that we can write it like this. We can write it instead as a1 vector, a2 vector, and so on up to a of n. So there's n columns of vectors. And this is actually pretty neat. This is actually something cool. This means actually all the vectors here, they are a member, of course. Let's see. Yeah, all the vectors here, of course, are a member of this guy. So they have, because they have the same amount, the amount of rows is, of course, determines this, the components of that vector, of course. But what is pretty neat here, as we can see, what was my conclusion here? I know that it's a span, but what I did, I wrote some horrible notes here. I just wrote, which means that all the vectors are members of, that's what I told here, defined as the linear combinations. Yeah, that makes no sense at all. That makes absolutely no sense. Okay. Okay, I think I can try and do this just without the notes. Let's see. I can at least state that from all of these vectors here, I can create a set, right? There's a set I can create of these vectors, right? I can state all of these column vectors as a linear combination, right? This will mean all the possible vectors I can create, right? As a linear combination here. So I forgot x2 there, and then I have xn, then an, right? These are all the possible vectors I can create with this linear combination. And actually, instead of just doing that, we can just think of it as the span, because as we know, the linear combinations of all of these column vectors is actually just the span. That's what it means, right? The span of two basis vectors in 2 dimension is, of course, the entire 2 dimension, right? It's the space R2, right? So here's the same idea here. So the span, we call this what do you call it? The column space of A. Column space of A. So the column space of A is just equal to, therefore, the span, we just use big S, the span then of A1, and then of course up to all the way up to AN, because that represents all the possible linear combinations of this column vector. That's what I was trying to say. I was pretty stupid there for a moment, but it's all right. Okay. And as we know, like we said earlier, that the span is, of course, a subspace. So that's the new theorem, of course, that the span of this, the span here is, of course, subspace, right? Because we know that the span of any 2 vector is a subspace. We already stated that earlier, right? So, of course, that's theorem 3. So that's pretty simple. Okay, Let's go to example 4. No, like not explicit, say column space. Yes, it's just a span, like I wrote there. Perfect. The column space of M by N matrix is a subspace of R of M. Of course, yeah, that is what I meant. Yeah, because we are spanning, right? Which type of vector we are spamming? Are spanning. Which are we spanning? We are spanning the vectors that has the amount of components that are rows, of course. Of course, they are going to be a subspace of Rm then. That makes sense. Okay. So now find a matrix such that W is equal to call A. This is also pretty simple. You can just, I can do this in my brain, we don't need to do this. You can just write this because I have, oh, we can do this. We are doing it. It's good practice, why not? Okay, I'm not going to be this thorough when I start the semester because you don't have the time to do that, but it's all right. 6a minus b, then I have a plus b, then I have minus 7a. Of course, then I have a comma b, and they are in R. Right, and we want to find a matrix A such that this guy satisfy call A, right? Okay, let's see if we can find a matrix A. The first thing you do is write this a little bit more clever. So what you do is just put A outside, then I have 6, 1, and then I of course have minus 7. Just add, and I just say B. Then I have minus 1, I have 1, and of course I have 0. Still have the same requirements. And now you can pretty much see it, because this is of course our matrix, because these two vectors here of course span this guy because we have constants in front of here. Right, so the column of A is here equal to W if A is equal to V1 and then V2, where this guy is V1 and this guy is V2. Nice. Okay, good. Yeah. Okay, you also have, if you have column space, you of course also have row space. And you can also write the row space pretty neat. So the row space, the same thing, just rows. So the row space, so let's say row of A, that's actually because if you transpose, you just flip it around like that. And then this is of course just the same as the call space of A transposed. So you have that as well. Cool. Then we have example 6, and then example 7 is pretty long. Okay, example 6. Okay, let A be equal to this. If the column space of A is a subspace of Rk, what is K then? Okay, if the column space of A is a subspace of Rk. Right, we have the column space, and these are of course in 3 dimensions because they are belonging to, of course, Rk, so k is equal to 3. But the null space of A is a subspace of, if the null space of A is a subspace of Rk, what is k then? Here we need a vector that satisfies that A times that vector is equal to 0. And that vector has to be input 1, 2, 3, and 4. So that is, of course, 4. Yes, as you see. And this, of course, is 3. Cool. 7. Was that the last example? Yeah. Oh, no, there's one, but I just explained that. Okay, this one is pretty long. Okay, with A, as in example 6, find a non-zero vector in call A and a non-zero vector in null A. Okay. So we need to move back here. In example 6, isn't that this guy? Yeah, I'm pretty certain that this guy. Or was it something else? Example 6. No, it's that big one. Ah, of course. I felt something was wrong there. Okay, so I just write that guy down. Let's see. A is 2, 4, minus 2, 1. Then we have minus 2, minus 5, 7, 3. Then we have 3, 7, minus 8, and then 6. That should be all right. Okay. All right, the first was finding a non-zero for the column space. That's pretty easy. Just pick the first one, for example. Was that correct? 2 minus 2, 3. 4 minus 5, 7. Minus 2, 7. Minus 8, 1, 3, 6. Yeah. Okay, so just pick that one. But to find the one that belongs to the null space is more tricky. So let's do that as well. Okay, the first thing you do, you can just row reduce it. So let's do that. So if I want to row reduce this guy, what I will do is take the guy in the middle and just add him to both the top and the bottom there. So this guy will be 1, and then of course I take this guy together, minus 5. 7, that's of course 2. 7, that's just minus 1. 3, 6, that's 9. And of course I get 0, neat, minus 5 and 4, that's minus 1. 7 and minus 2, that's of course 5, and 3 and 1, that's 4, like that. Okay, now let's continue. I of course, I use the middle one, so now I can use the bottom one and getting rid of that middle one. So I have 1, 2, minus 1, 9, of course. Does that make sense? I'm going backwards, am I? I use that middle one to reduce this guy. Does it make sense then to do? Yeah, that makes sense as well. Right. Yeah, I can do that. That's actually, maybe that's stupid. I think it still works, even though it's a little bit stupid. Because you add and do the same thing again. We can just do it and see. Okay. If I now use 1 multiplied by 2, that's 0. That's 0 multiplied by 2. That's minus 1, of course. I multiplied by u by 2. That's of course 5. I multiply u 9 there by 2. That's 18. And 3, that's 21, like that. Nice. 0. And of course I can just multiply 1. That's just stupid. Minus 5 and minus 4, like that. Okay. Pretty neat. Then all of these are okay. Now I can just add the middle row to the top row. I get 0, minus 1 here, 5, 21. If I add that to the top row, I have 0, 0, 0, 21, and 17, like that. I have, of course, 1. I should add that one as well. So just multiply by 2, 1, 0, multiply that guy by 2, that's 10. And that's of course just 9 multiplied 21 by 2. That's stupid, that's 42. Have I done something incredibly stupid here? Why the hell do I have 21? 21. I multiply 21 by 2, that's 42. That doesn't seem correct at all. Did I miss something? That seems pretty stupid. Yeah, just let us run with it. Okay, 21 by 2, that's 42. And of course, added with 9, 42, and that's 51. 51, that seems, yeah, that seems like I've been doing something very wrong. Okay. All right. Yeah, that seems like something here went wrong for some reason. What the heck have I done? I did multiply u by 2, u by 2. That's the 21 shouldn't be there, I think. Where did I get that 21 from? Let's see. I had 3 and 6. Yeah, I did something stupid here. Let's do it again. That was pretty bad. That's why we're doing this. It's always good to do some exercise. Okay, what I did, I used that middle one, which was stupid. That makes absolutely no sense. I could just use the... No, but that middle one isn't that bad. Why did I wasn't satisfied with that? Okay, let's do it. Let's use the top one then. I used the top one too. Do I want the top? But that's also not too good either. Do you know what? I do what I always do instead. I divide this guy by 2. So I have 1, I have 2, then I have -1, and then I have 1/2. And then I reduce. I hate doing anything else. I multiply u by 2, that's 0. I multiply u by 2, of course, then I get 4, and then of course this is just -1. I multiply u by 2, that's -2. I know this seems stupid, but that's my brain works a lot better this way. I multiply u by 2, that's -2. -2 and 7, of course that is 5. And then I multiply u by 2, that's just 1, and 1 and 3, that's of course just 4, like that. Okay, now I can do the last one as well. So I have 3 there, I multiply u by -3, so 0. I multiply the first one by -3, that's -6, so 1. I multiply this guy, -1, by of course -3, that's of course 3, and 8, that's -5. And I multiply the first one by -3, that's -3 over 2 and 6. Oh, I hate this. I done something. What did I miss last time? I hate things like this. These are the worst. I have -3 over 2 plus 6. Oh, this is not fun. I don't like this at all. Okay. Do I want this? I get, of course, 12 over 2. This is so boring. I hate this. Because now my equation is 9 over 2. I don't... Oh, my days. What have I done? Okay, I'm not going to do that. God damn. Okay. Let's try it again. That was bad. It's alright. Just do it again. Okay. Do what you did first. I think that's the best idea. Right. This should be easy. Yeah, that should be easy. Let's do that. I use -2 and add together there. So I get 1. -5 and 7, that's just 2. 7 and -8, that's just -1. 3 and 6, that is 9. Of course, I go upwards, so -2 and 2, that's 0. -5 and 4, of course. Yeah, do I want that? Yes. I can keep it like... Oh, I know what I do. I do the opposite way. I do 2. Okay, I do that. I do 2 and then -2, 0. Then I do 4 and -5, -1. I do -2 and 7. What is my brain smoking? And then I do 1 and 3, and that's of course 4. Yeah, now things makes more sense, I think. I think this will work now. Yeah. It's good to do some workout. Okay, I multiply the last row by -2. 0, -2, 0, -2, -2. Yeah, that's of course 0 again. Is that correct? Yeah. And then -2, that's of course just -18. And that's of course +1, so -17. I think this is correct as well. Nice. 0, 1, -5, and then -4, like that. Neat. This looks a lot better. 2, and then -1, and then of course 9. Yes. Yes. Ah, damn, that was super annoying. I can do below. I move this guy up. 1, 2, minus 1, 9. Then I have 0, 1, minus 5. Then minus 4. 0, 0, and of course 17. There's no point, so just 1. Nice. It's all right. Okay, now I can just use 1, and I can get rid of these guys. Nice. Finally. All right. Okay. That should be mostly correct. I can also get rid of this guy. Can't I do that? That 2 there. Yeah, I can do that. If I take 1 here, multiply by minus 2. Yeah, I can do that. So 0, 1, minus 5. Oh, that was not good. 0, 1, minus 5, and then 0. I have 1, multiply by minus 2, that's 0. Multiply by minus 2, that's 10. 1, that's 9. That's 0. This is correct. Yes. Yes, that's how it should be. Nice. Okay. Yeah, that is good. Okay, so now we have to, of course, solve. So now I did all this stupid thing here, but I wanted to know if I could find a non-zero vector that was in the null space. That was the idea now. So what you do then is that you just extend this guy to see if there's a solution. That is why matrices are so nice. So what you can do is just move this guy here and test if this is true. And this is just a set of equations. So we actually just have x1. Then we have plus 9 x3. All right, and that's just equal to 0. Then I have, of course, x2. I should have, just to make this a little bit more aligned, like that. I should like that as well. Yeah, that makes 0. So just 0 plus this guy and then plus 0. Then it makes more sense. Then I have 0 plus then x2 minus 5x3 plus 0 again is equal to 0. And then the last one is that x4 has to be equal to 0. So now we have a system of equations, and we have x1 is equal to 9 x3. Did I miss something here? No. I think it's all right. Yeah, it's all right. Yeah, it's all right. 9x3. Then I have that x2 is equal to minus 5, not minus 5. My calculation here is pretty stupid now. Okay. x3 like that, and of course this guy should be minus. And of course x4 is equal to 0. Then you could see that x3 now is a free variable. Why is that? There's no pivot here. This is not a pivot column. This is, and this is. That means that x3 isn't bound to anything. If it isn't bound, it's free to choose. Okay, now since that is true, we can make a vector. So let's state that x3 is equal to 1. Then we have that our vector v1 is just equal to minus 9. Minus 9, it's equal to 5. x3 is equal to 1, and 4 there. So this is our non-zero vector that lives in the null space. Awesome. Pretty neat. Okay, let's see. What is the next thing to do here? Yeah. Example 8, I just told myself to just explain this. With A, as in example 6, let U and let V determine if U is in null A. No, we are not going to do that. It's enough for me now. Okay. I can do task 23 and 24. That works. That's a part of the tasks I'm supposed to do. Let's see. And those are pretty easy. We are not going to do that. Yeah, you can let A be equal to this and W be equal to this. Determine if W is in call A, is W in null A. If it's in null A, you can just do the same thing we did here, but now you can just calculate it directly. take 2 and well, you can see it instantly. If I take 2 there, 2 goes here and 1 goes there, 0. 2 goes there, 1 goes there, 0. So it's in null A. And as well, you can move out 2 and 1. I can do that. So I can do another type of solution to this problem. I don't think you're supposed to solve it like I do now, but who cares? My solution is pretty valid. -3, 12, and 6. I want to check if V is in call A. So W, I mean W, not V. 2, 1, is this in call A? Right. That's our question. So what you can do is you can write, if I write 2, 1 here, right? I can just do it like this. I can say -3, 2, 1, plus, of course, 6, and then 2, 1. So not only is it's actually a basis, as you see. We have a linear combination here, and of course the span of these 2 columns, which is just that column, is of course that call of A. So that's all right. Pretty neat, because 2, 1 actually spans the whole of this guy, right? Okay, and you do the same thing for here. I'm not going to do that. It's enough now for today. Okay, it was a bit of a struggle, but that's good. That's the point of doing all of this. You're supposed to struggle. That's all right. Not all the time it goes just easy on itself, but that's all right. Okay, see you tomorrow.